So in grade school, we're usually taught that there's three states of matter, like solids, liquids, and gases. But maybe somewhere along the line we learned about plasmas, and we're like, oh my god, we're lied to. There's four of them. And now anytime that somebody says that there's three states of matter, you're like, oh my god, but plasmas. It's really annoying. Um, and then maybe after that you'll learn that there's more than just the three and plasmas. There's other exotic states of matter too. And today I want to talk about one of those exotic states of matter, and those are Bose-Einstein condensates. And they're super cool. Um, so what is this? This is when you take a bunch of bosons and you pull them way down so they collapse into the lowest possible energy state. And they're super cool. Their discovery is really historically interesting, and you should totally look into it. Bose was a super cool guy. And they were first created in 1995 with some rubidium atoms in the lab. And then later that year with sodium. And this got the 2001 Nobel Prize. And we do some interesting physics with them. But today I want to focus on some math associated with these and help us really understand why this happens. So we're going to start by looking at the quantum energy levels that the atoms can occupy in this condensate. So we're going to imagine some helium-4 atoms. These are bosons, and they're confined in a cubic box of some side length L. And we can define their quantized energy level of each atom. It can be given by h bar squared over 2m pi over L squared, nx squared plus ny squared plus nz squared. Cool. Now, the ground state of this is going to be when nx equals ny equals nz equals 1. So this is going to be E11 equals h bar squared over 2m pi over L squared. 1 squared plus 1 squared plus 1 squared. Oh, sorry, I wrote this really poorly. 1 squared plus 1 squared plus 1 squared is 3. So there's epsilon 111. Epsilon 211 is going to be h bar squared over 2m pi over L. And this time it's going to be 2 squared plus 1 plus 1. So we're going to have a factor of 6. And that's our next lowest orbital. So if we want to get an excitation energy, delta epsilon, we do epsilon 211 minus epsilon 111, which is going to give us 3 h bar squared over 2m pi over L squared. So we'll say that the mass of a helium-4 atom is 6.6 times 10 to the negative 24 grams. We'll call L 1 centimeter. And if we do this, we get the delta epsilon over kb is about 1.8 times 10 to the negative 14 Kelvin. Alright, so let's apply this to a Bose-Einstein distribution to see how many atoms occupy the first excited state. So let's say delta epsilon tau 1 over e delta epsilon over tau minus 1. We'll say we're pretty cold. Tau is 1 millikelvin. Then this becomes about 5 times 10 to the 10th. Alright, and you might be thinking damn, that's a lot of excited atoms. But we want to think about what the total number of atoms is in this system to start with. So we'll say a mole of atoms, that's 6.022 times 10 to the 23 or so, right? So we'll say we have less than a mole. We'll say we have 10 to the 21 atoms in our system, right? So the fraction of our atoms in the first excited state, F over n, will be 5 times 10 to the 10 over 10 to the 21 atoms is going to be 5 times 10 to the negative 11 excited atoms. And this is a tiny number. This is essentially 0. So that's why we say all of the atoms are in the ground state. Most of them are. And this is what we mean by a Bose-Einstein condensate. All these bosons piling into a ground state, doing weird stuff. Super cool. Physics is so fun. Okay. I hope that helps. And bye.